After studying this module, you shall be able to learn about methods for characterizing molecular weight, understand the concept of viscosity, learn about the viscosity method for determining molar masses of macromolecules, learn about the empirical correlations between intrinsic viscosity and molecular weight for linear polymers, learn about the ultracentrifugation, which involves the sedimentation velocity method and the sedimentation equilibrium method for determination of molar mass of polymers. A specified polymer material is generally a mixture of molecules of identical or nearly identical chemical structure and composition, but differing in degree of polymerization or molecular weight. The molecules produced by polymerization reaction have chain lengths that are distributed according to a probability function that is governed by the polymerization mechanism and by the condition prevailing during the process. Hence, the concept of average molecular weight assumes importance and becomes very much relevant in case of macromolecules. Some of the commonly used averages for describing the distribution of molecular masses of polymers are as follows. Number 1, number average molar mass Mn bar equals to summation Ni Mi divided by summation Ni, given by equation 1, where Ni is the number of molecules each having molar mass Mi. Number 2, mass average molar mass Mw bar equals to summation Wi Mi given by equation 2, where Wi is the mass fraction and Mi is the molar mass. Number 3, Z average molar mass Mz bar equals to summation Ni Mi cube divided by summation Ni Mi square given by equation 3. And 4, viscosity average molar mass Mv bar equals to summation Ni Mi to the power a plus 1 divided by summation Ni Mi whole to the power 1 by a, given by equation 4. Some of the classical methods used for determination of molecular weight of polymers are osmometry, light scattering technique, analytical centrifugation, intrinsic viscosity method. The number average molecular weight assumes prime importance in the context of studies of solution properties that go by the name of colligative properties, viz. Vapor pressure lowering, freezing point depression, boiling point elevation, and osmometry. On the other hand, the weight average molecular weight assumes importance in the context of various bulk properties of the polymers, particularly the rheological and resistance properties. Now, we shall learn about the methods for characterizing the molecular weights. Analytical techniques for the determination of molecular weights can be classified into primary and secondary techniques on the basis whether or not standards are needed to calibrate the instrument. Most of the primary techniques are based on the colligative properties such as depression in freezing point, boiling point elevation, and osmotic pressure. Intrinsic viscosity is theoretically a primary technique, but dilute solution viscosity method yields viscosity average molar mass, which is not an absolute value but a relative mass based on prior calibration with known molar mass for the same polymer solvent temperature conditions. Primary techniques involve a significant effort and yield only one moment of molecular weight. Therefore, these techniques are not used on a routine basis. On the other hand, in relative techniques, sample preparation and actual measurement are much simpler and reproducible. The most commonly used secondary technique is gel permeation chromatography, also known as high pressure liquid chromatography. Now, we shall have a look at the viscosity and molecular size. Fluids resist a flow gradient. This resistance produces a frictional force known as a viscous force proportional to the area of contact, A, between the flowing regions and to the velocity gradient dV by dx. The constant of proportionality is called the coefficient of viscosity abbreviated as eta. Hence, viscosity is defined as the property of a fluid that resists the force tending to cause the fluid to flow. The unit of viscosity is poise and F is equal to eta A dV by dx as shown in equation 5. Looking at the origin of viscosity, viscosity is a property of fluids, that is, liquids and gases. For liquids, it is dominated by short-range attractive intermolecular forces, the effects of which are hard to model. For gases, viscosity arises from momentum transfer between layers of moving molecules. The kinetic theory of gases gives the following formula for the viscosity of a gas, that is, eta is equals to square root of mRT divided by sigma to the power 4 pi to the power 3 Na square, as shown in equation 6, where m is the molar mass, r is the gas constant, sigma is the molecular diameter, Na is the Avogadro's number. For example, for helium gas at 298.15 Kelvin, this equation predicts a coefficient of viscosity of 198 micropoise. Perhaps the most important result of the kinetic theory derivation is the prediction that the viscosity of a gas increases with temperature and molar mass. It is well known that viscosity of a typical liquid decreases with temperature. The usefulness of solution viscosity as a measure of polymer molecular weight has been recognized ever since early work of Staudinger 1931. Solution viscosity is a measure of the size or extension in space of the polymer molecules. It is empirically related to the molecular weight of linear polymers, the simplicity of the measurement, and the usefulness of the viscosity molecular weight correlation is extremely significant that viscosity measure constitutes an extremely valuable tool for the molecular characterization of polymers. Now, we shall have a look at the experimental methods. Measurements of solution viscosity are usually made by comparing the efflux time T required for a specified volume of polymer solution to flow through a capillary tube with the corresponding efflux T naught of the solvent. From T naught and the solution concentration, we can derive several quantities whose defining equations and names are given in table. The table shows the nomenclature of solution viscosity. Dilute solution viscosity is generally measured in capillary viscometers of the Oswald, Fenske or Ubel-Hob. The latter has an advantage that the measurement is independent of the amount of solution in the viscometer. Moreover, measurements at a series of concentrations can easily be done by successive dilutions. Figure shows the capillary viscometers commonly used for the measurement of polymer solution viscosities. A is the Oswald Fenske viscometer and B is the Ubel-Hob viscometer. Now we shall have a look at the treatment of data. From the various methods used for determination of molar masses of macromolecules, the viscosity method introduced by Staudinger is the most frequently used method utilized in research. Accurate measurement of absolute viscosity is difficult, therefore it is convenient to measure the relative viscosity. Hence, relative viscosity is defined as eta relative equals to eta by eta naught, which is approximately equals to T by T naught as shown in equation 7, where eta and eta naught are respectively the viscosity of the solution and the viscosity of the solvent. Relative viscosity can be related to other quantities such as specific viscosity, abbreviated as eta Sp, reduced viscosity, abbreviated as eta reduced, and intrinsic viscosity eta through the relations. Eta Sp is eta relative minus 1 as shown in equation 8. Equation 9 shows eta relative is equal to eta Sp by C, and the intrinsic viscosity is eta Sp by C, where limit of C tends to 0 as shown in equation 10. In the mentioned equations, C is the concentration of the polymer. Moreover, these equations do not have units of viscosity. In 1906, Einstein derived a relation between the viscosity of the dilute suspensions of hard spherical molecules and the volume fraction phi of the solute molecules. This is given by equation 11 as eta equals to eta naught into 1 plus 2.5 phi. Rearranging equation, we get eta by eta naught equals to 1 equals to eta sp equals to 2.5 phi as equation 12. Hence, from equations 10 and 12, we get eta, the intrinsic viscosity, equals to limit of eta sp by c, where limit c tends 0 equals to 2.5 phi by c, as shown in equation 13. It is, however, very difficult to measure phi, the volume fraction of the polymer molecules in solution. Viscosity data as a function of concentration are extrapolated to infinite dilution using the Huggins equation. The Huggins equation is shown by equation 14 as eta sp by c equals to the intrinsic viscosity plus k prime intrinsic viscosity squared times c, where k prime is the constant for a series of polymers of different molecular weights in a given solvent. The alternative definition of the intrinsic viscosity leads to the equation given by Kremer in 1938, as shown in equation 15 as ln of eta reduced by c equals to intrinsic viscosity plus k double prime eta square times c. Both these equations are applicable only in dilute solutions. For many polymers, k prime equals to 0.4 plus minus 0.1 and k double prime is equals to 0.50 plus minus 0.05, where k prime minus k double prime is equals to 1. The slopes of the lines vary as eta square as required by equations 14 and 15 for polymer species of different molecular weight in the same solvent. The plots of eta sp by c and eta reduced by c versus c gives the straight line which conform to the above mentioned equations. Now we shall see the empirical correlations between the intrinsic viscosity and molecular weight for linear polymers. Staudinger in 1950 established that for a series of samples of the same polymer in a given solvent and at a constant temperature, the intrinsic viscosity or the viscosity numbers is related to the molar mass of the polymer by the equation known as Mark-Cohen-Howing-Sakurada equation, formerly called Staudinger equation. The intrinsic viscosity is equals to K into m viscous bar to the raised to the power A, given by equation 16, where m viscous bar is the viscosity average molar mass of the polymer and K and A are constants, usually determined by intrinsic viscosity measurements on a series of polymer samples for which the molar mass has been determined by a different method, say the light scattering method. The value of the exponent A depends upon the geometry or the shape of the macromolecule. The more elongated a macromolecule, the more effective are the higher molar mass fractions in reducing the viscosity of the solution. The values of A vary from 0.5 to 1. For polymers behaving as random coils, A is about 0.8, and for globular proteins possessing a compact structure, it is about 0.5. Note that intrinsic viscosity has the dimensions of reciprocal density and hence its units are centimeter cube per gram. Taking logs of both sides of equation 16, we get ln eta equals to ln k plus A times ln m viscous bar as shown in equation 17. Equation 17 shows that log plot of eta versus m viscous bar gives a straight line with slope equals to A and intercept equals to ln k. Thus, the constants A and k can be easily determined. Knowing the values of A and k, the viscosity average molar mass m viscous bar can be determined from intrinsic viscosity measurements. Now, we shall study about ultracentrifugation. The rate of sedimentation of suspended particles under the action gravity is very small. However, it can be increased considerably by applying the ultracentrifugation technique developed by Swedberg. A particle sedimentation in a centrifugal field is subjected to an acceleration given by omega square x, where omega is the angular velocity of the centrifuge given by 2 pi into the number of revolutions per second, and x is the distance of the particle from the axis of rotation. The rate of sedimentation can therefore be increased considerably by increasing the number of revolutions per second. In some of the ultracentrifuges, the number of revolutions is as high as 1000 per second. If the particle is at a distance of 10 cm from the axis of rotation, that is x is equals to 10 cm, the acceleration in the centrifugal field would be equal to omega square x, which is equal to 2 pi into 1000 whole square into 10 equals to 3.94 into 10 to the power 8 centimeter per second square. This is nearly 4 lakh times greater than the acceleration due to normal gravity, which is only 981 centimeter per second square. The rate of sedimentation therefore can be raised by 4 lakh times the normal rate. When a polymer solution is placed in the cell of a centrifuge, the polymer molecules tend to distribute themselves during rotational perpendicularly to the axis of rotation throughout the cell in accordance with their individual molar mass. At some constant force, the larger molecules move rapidly towards the periphery, the largest molecules being found nearest the periphery at equilibrium. If a strong beam of light passing parallel to the axis of rotation and perpendicular to the axis of the cell is used to measure the refractive index, then the concentration of the polymer solution any given section can be measured. This enables the determination of the velocity of the molecular movement towards the periphery at equilibrium. The ultracentrifugation technique for the determination of molar mass of a polymer may involve A. The sedimentation velocity method, or B. The sedimentation equilibrium method. While the first method yields the number average molar mass, the second method yields the mass average molar mass. First, we shall discuss about the sedimentation velocity method. Consider a polymer solution being spun in a centrifuge tube under the influence of a very strong gravitational field. The centrifugal force acting on the solute particle of mass m at a distance r from the center of rotation is given by m omega square r, where omega is the angular velocity of the rotor in radians per second. The particle is also subjected to a buoyant force in addition to the centrifugal force, so that the resultant force acting on the particle is given by resultant force is equals to centrifugal force minus the buoyant force, which is further equals to m omega square minus ms omega square r, as shown in equation 18, where ms is the mass of the displaced solvent. If rho is the density of the solvent and V the volume of the solute particle, then ms is equals to V times rho. However, the measurement of V is extremely difficult. Hence, it is customary to define a quantity V bar, the partial specific volume, as the increase in volume when 1 gram of a dry polymer solute is dissolved in very large volume of the solvent. Then obviously the quantity mV bar will represent the increase in volume obtained on adding a solute particle of mass m to the solvent. In other words, mV bar equals to V. Hence, equation 18 transforms to the resultant force equals to m omega square r minus m omega square r V bar into rho, which can be further written as m omega square r into 1 minus V bar rho, as shown in equation 19. This resultant force, according to the Newton's second law of motion, will cause the solute particles to accelerate. However, the acceleration in this case will not last long, since the medium exerts a frictional force on it, which is proportional to the sedimentation velocity dr by dt. Thus, the frictional force is equals to F times dr by dt, where F is the frictional coefficient. The frictional force acts in the opposite direction to the resultant force. When the steady state is reached, we have from equation 19 and 20 F into dr by dt equals to m omega square r into 1 minus V bar rho. Equation 21 can be rearranged to give a quantity S, defined as S equals to sedimentation velocity or the centrifugal acceleration. That is, S equals to dr by dt divided by omega square r, which is equal to m into 1 minus V bar rho divided by F, which can be further written as Mn bar divided by Na into 1 minus V bar rho divided by F, as shown in equation 22. The quantity S is called the sedimentation coefficient. It is the sedimentation rate for a unit centrifugal acceleration. For a given molecular species in a given solvent at a given temperature, S is a constant. It is expressed in the unit Swedberg, named after the Swedish chemist. For a spherical polymer particle of radius r, the frictional coefficient F is related to the coefficient of viscosity of the solvent eta by the Stokes equation, that is, F equals to 6 pi eta r. This is our equation 23. Hence, from equation 22 and 23 we get Mn bar equals to S Na into F divided by 1 minus V bar rho, which can be further written as 6 pi eta r S into Na divided by 1 minus V bar rho, as shown in equation 24. Unfortunately, the above relation applies only to the spherical molecules. For polymers which are shaped like rods, ellipsoids or coils, the Stokes law does not apply. Hence, F must be determined experimentally. This is usually done by diffusion experiments, which are not simple to carry out, but which have the advantage that the phenomena of diffusion is very similar to that of sedimentation, so that one can expect the frictional coefficient F determined from diffusion to be identical with the frictional coefficient F, which is characteristic for sedimentation. The relationship between the experimentally determined diffusion coefficient D and the frictional coefficient F is given by Stokes-Einstein diffusion equation, that is, D equals to RT divided by Na times F, which can be further written as KT divided by F, as equation 25, where F is KT by D. Thus, from equation 24 and 26, we get Mn bar equals to S into Na into KT divided by D into 1 minus V bar rho, which can be further written as S into R into T divided by D into 1 minus V bar rho, as shown in equation 27, which is called the Swedberg equation for determination of molar mass of the polymer. The sedimentation coefficient S and the diffusion coefficient D must be corrected to the same temperature, usually 20 degrees Celsius. If both these coefficients are concentration dependent, then their values must be extrapolated to zero concentration. Now we shall have a look at the experimental setup. The ultracentrifuge is shown schematically in figure. The measurement of sedimentation velocity in the ultracentrifuge leads to the determination of the sedimentation coefficient. The dilute solution of the polymer contained in a cell is introduced into the rotor of this ultracentrifuge. The cell is filtered with 2 quartz windows to permit photographing of the solution. As rotation in the centrifuge proceeds, the polymer molecules slowly sediment with constant velocity under the influence of the gravitational force towards the bottom of the cell. Depending upon the homogeneity of the dissolved particles, one observes at the upper edge of the cell an almost sharp boundary against the pure solvent, which, as centrifugation continues, moves towards the bottom of the cell. This process may take several hours. The velocity with which the boundary moves is the sedimentation velocity. It is, however, not possible to obtain a very sharp boundary between the solution and the solvent layer above it, because the separation is smeared out through rediffusion of the sedimenting particles, and the boundary for the non-homogeneous system is spread out further, since the components with low molar mass remain behind during the sedimentation, while the components with higher molar mass sediment more quickly. Now, by definition, S is equals to dr by dt divided by omega square r, or if the boundary is at a distance r1 from the axis of the cell ultracentrifuge at a time t1 and at a distance r2 from the axis at time t2, then the integration of the equation yields integration from t1 to t2 of S dt equals to 1 by omega square integration from r1 to r2 of dr by r, as shown in equation 29, or S into T2 minus T1 equals to 1 by omega square ln R2 by R1 as shown in equation 30. Or S can be written as 1 by omega square into T2 minus T1 into ln R2 by R1 as shown in equation 31. The sedimentation coefficient for a given macromolecule is independent of the angular velocity omega of the rotor, the reason being that as omega square r increases, dr by dt increases too, so that the ratio of the two remains constant. The sedimentation coefficients for proteins lie in the range of 10 to the power minus 11 seconds to 200 into 10 to the power minus 13 seconds. Now we shall have a look at the second method, which is the sedimentation equilibrium method. In the sedimentation equilibrium method, the rotor speed is lower, about 10,000 rpm, than in the sedimentation velocity method, where the rotor speed was of the order of 60,000 rpm. When an equilibrium between sedimentation and diffusion is reached, there is n net flow. Now, according to the Fick's law of diffusion, the rate of diffusion, that is the number of solute particles n crossing a vertical plane per second from higher concentration to lower concentration, is directly proportional to the area of cross section A and the concentration gradient dC by dr. That is, rate of diffusion is equals to dN by dt, which can be written as minus dA into dC by dr, where d is the diffusion coefficient in the units of centimeter square per second. For solute molecules flowing through the unit area, A is equals to 1 and dN by dt is equals to minus d dC by dr as shown in equation 33. The negative sign in this equation 33 has been omitted since the concentration gradient increases with increasing value of r. Since from the Nernst-Einstein diffusion equation d equals to kT by F, hence dN by dt is equals to kT by F dC by dr, which can be further written as RT by NA F into dC by dr as in equation 34. From equation 21, the rate of sedimentation of the polymer solution is given by dr by dt equals to m omega square r by F into 1 minus V bar rho as shown in equation 35, or C times dr by dt equals to m omega square Rc by F into 1 minus V bar rho as shown in equation 36. Since at equilibrium the diffusion rate is equal to the sedimentation rate, we have from equation 34 and 36 dN by dt equals to C into dr by dt, or RT by NAF into dC by dt equals to m omega square Rc by F into 1 minus V bar rho as shown in equation 38. Cancelling F from both sides of equation 57, setting m equals to mm bar by Na and separating the variables, we have dC by C equals to mm bar times omega square r into 1 minus V bar rho divided by RT into dr as shown in equation 39. Integrating this, we get equation 40, or ln C2 by C1 equals to mm bar into omega square into 1 minus V bar rho by RT into R2 square minus R1 square as shown in equation 41, which can be rearranged to give mm bar equals to 2 RT ln C2 by C1 divided by omega square into 1 minus V bar rho into R2 square minus R1 square as shown in equation 42, where omega is the angular velocity of the rotor in radians per second, rho is the density of the solution, C1 is the concentration at a distance R1 and C2 is the concentration at a distance R2 from the axis. The concentration ratio C2 by C1 is determined by the photometric measurement. From equation 42, we see that a plot of ln versus r square should be linear with slope equals to mm bar into omega square into 1 minus rho into V bar divided by 2 RT. Thus, from the measurement of the slope, mm bar can be calculated. Unlike the sedimentation velocity method, this method does not require prior knowledge of the shape of the macromolecule or its diffusion coefficient. Hence, it is one of the best methods for determination of molar mass of the polymers. However, the sedimentation of equilibrium method requires a long time, up to several days or weeks for completion. Now, we shall summarize what we have learnt in this module. The number average molecular weight assumes prime importance in the context of studies of solution properties that go by the name of the colligative properties, that is, vapor pressure lowering, freezing point depression, boiling point elevation, and the osmometry. On the other hand, weight average molecular weight assumes importance in context of various bulk properties of the polymers, particularly the rheological and the resistance properties. Viscosity is defined as a property of a fluid that resists the force tending to cause the liquid to flow. F is equals to eta into A into dV by dx. The constant of proportionality eta is called the coefficient of viscosity. Formula of viscosity of gas is given by eta equals to square root of mRT divided by sigma to the power 4 pi to the power 3 Na to the power 2. Solution viscosity is measure of the size or the extension in space of polymer molecules. Dilute solution viscosity is generally measured in capillary viscometers of Oswald-Fenske or Ubel-Hud viscometers. Viscosity data as a function of concentration are extrapolated to infinite dilution using the Huggins equation. Huggins equation is eta Sp by C equals to eta plus K prime eta square times C. The alternative definition of the intrinsic viscosity leads to the equation given by Kramers as ln eta reduced by C equals to eta plus K double prime eta square times C. Both these equations are applicable only in dilute solutions. The plots of eta Sp by C and eta reduced by C versus C give straight line. The slopes of the line vary as eta square. The intrinsic viscosity or the viscosity numbers is related to the molar mass of the polymer by the equation known as Mark-Cohen-Howing-Sakurada equation, formerly called as Staudinger equation, given by eta equals to K into m viscous bar to the power A, where m viscous bar is the viscosity average molar mass of the polymer and K and A are constants. The rate of sedimentation of suspended particles under the action gravity is very small. However, it can be increased considerably by applying the ultracentrifugation technique developed by Swedberg. The ultracentrifugation technique for the determination of molar mass of polymer involve A. the sedimentation velocity method and B. the sedimentation equilibrium method. Sedimentation velocity method uses the Swedberg equation for the determination of molar mass of a polymer, that is Mn bar equals to SNA-KT by D into 1 minus V bar into rho equals to SRT divided by D into 1 minus V bar rho. By using the sedimentation equilibrium method, molar mass of polymer can be determined by mm bar equals to 2 RT ln C2 by C1 divided by omega square into 1 minus V bar rho into R2 square minus R1 square, where omega is the angular velocity of the rotor in radians per second, rho is the density of the solution, C1 is the concentration at a distance R1 and C2 is the concentration at a distance R2 from the axis.